Welcome to the High Voltage AI Podcast. This week, we're doing something a bit special for you electric utility engineers out there, pulling directly from the High Voltage AI newsletter on Substack. Now, often in the newsletter, we get really granular on overhead and underground construction, the why and the how. But today, Monday, we're starting the week with a topic that's really reshaping the whole power system landscape. We're doing a deep dive into grid forming versus grid following, the fundamental difference reshaping power systems. And this is just day one. Tomorrow, Tuesday, we'll get into the nuts and bolts of control system architecture, how synthetic inertia actually works. Wednesday is all about system integration challenges. Then Thursday, real-world applications. And we wrap up Friday looking at career opportunities in this grid forming era. So a full week. But let's kick off today by setting the scene, painting a picture of why this shift is so critical. Picture this. It's nearly 2 a.m., February 15th, 2021. Ear-cut operators are staring at their screens, and the system frequency is just plummeting. It hits 59.302 hertz. Think about that, just 0.098 hertz away from triggering automatic load shedding. Blackouts for millions.
It's incredibly close, a knife's edge, really.
And it stayed below that critical 59.4 hertz mark for over 4 minutes. 4 very long minutes. Ultimately, they had to manually shed 20,000 megawatts of load. That wasn't just, a bad night. It was the largest controlled load shedding event in U.S. history.
And what's crucial to grasp there, Alex, beyond the obvious issues like frozen equipment, was the really severe loss of grid inertia. That's the system's natural cushion, right? The kinetic energy stored in all those big spinning traditional generators.
The shock absorbers, basically.
Exactly. As those tripped offline, the grid lost that inherent stability, that ability to ride through disturbances.
So that really crystallizes the challenge, doesn't it? As we bring more and more renewables online, which often use grid-following inverters, who or what provides that essential grid stability? It's not just about generating power anymore.
No, it's fundamentally not. That event really underscored a major transition. We're moving away from a grid where stability was almost a given, a byproduct of those large synchronous machines, to one where power electronics, specifically these grid-forming inverters, have to actively create that stability. It's not just an upgrade. It's a whole new way of thinking, a paradigm shift.
Okay, paradigm shift. Let's unpack that. To really get it, we need to start with the incumbent, the standard we've had for years. Grid-following inverters. How do they actually work? What's their core principle?
Right, so grid-following inverters, which you find in most existing solar and wind farms, operate as controlled current sources. The name says it all, really.
Yeah.
They follow the grid. Their entire operation depends on the grid already being stable and providing a voltage reference.
They need something to follow.
Precisely. They use something called a phase-locked loop, or PLL, to constantly track the grid's voltage and frequency and synchronize their current injection to it. They inject real and reactive power based on commands, but they absolutely need that strong voltage signal from nearby rotating machines. We often quantify this using the short-circuit ratio. They typically need it to be higher than 2.0.
Meaning the grid needs to be stiff enough from traditional generation.
Exactly. They're essentially passive supporters in terms of grid stability. They can't set up the voltage or frequency on their own.
Okay, so if they're followers, what other key technical traits that engineers need to know, especially regarding stability?
Well, the control mode, as I said, is current source, tied to that PLL synchronization. A major implication is that their performance really degrades in weak grid conditions.
Weak grids meaning areas far from those big generators.
Correct. Areas with low short-circuit ratio. In those conditions, grid-following inverters can struggle, sometimes even leading to instability. Then there's fault response. Their contribution during a fault is quite limited, usually only about 1.2 to 1.5 per unit.
And maybe just quickly explain per unit for folks less familiar with that term.
Good point. Per unit is just a way to normalize values. We pick a base value like the inverter's rated current and express everything as a fraction or multiple of that base. So 1.5 per unit fault current means the inverter provides 1.5 times its normal rated current during a fault. It simplifies comparing equipment of different sizes and voltages.
Got it. So their fault current is relatively low compared to traditional generators.
Much lower, yes. And critically, they provide zero inherent inertia. Any frequency response they offer comes purely from program control algorithms reacting to grid measurements, not from physical energy storage. And they have no black start capability. They can't energize a dead grid.
It really sounds like they were tailor-made for the old grid, the one dominated by synchronous generators. Why did they work so well in that context?
They worked because the synchronous generators did all the heavy lifting for stability. Those big machines provided the strong voltage reference the PLLs needed. They provided the natural inertia from their spinning mass, the high fault current needed for protection systems to operate reliably, and inherent voltage regulation. Grid-following inverters could just focus on injecting their power. They were passengers, in a sense.
Okay, which brings us squarely to the revolution. Grid-forming inverters. If the old way was following, what's the fundamental change here?
This is the game changer. Grid-forming inverters operate as controlled voltage sources. This is the key difference. They can independently establish and maintain the grid's voltage and frequency. They don't need an external reference waveform to follow. They create it.
They build the grid themselves, locally at least.
That's a good way to put it. They operate autonomously, setting the voltage, magnitude, and frequency. They often do this by using complex control algorithms that emulate the behavior of traditional rotating machines, sometimes called virtual synchronous machines, or VSMs.
Okay, so VSM, that sounds like where the synthetic inertia comes in. They're not just making power, they're actively creating the stability characteristics we used to get from spinning metal.
Precisely. They provide frequency stability through these algorithms, mimicking inertia. And remarkably, they can often respond faster than physical mechanical inertia. And here's another key difference. Unlike grid following, their performance tends to improve in weak grid conditions, not degrade. They can operate stably even when the short circuit ratio is down around 1.0.
That's counterintuitive, but makes sense if they're creating the reference.
Exactly. And yes, a massive capability is black start. They can actually energize a dead bus and start rebuilding the grid voltage from scratch.
Huge for resilience. What about their other technical specs?
Well, the control mode is voltage source, autonomous frequency, and voltage control that's foundational. Fault current is programmable, often up to 2.0 per unit, so a bit higher than grid following and controllable. The inertia emulation is software-defined. You can set the inertia constant H, typically somewhere between 2 and 10 seconds, and adjust it. And crucially, for things like microgrids or restoration, they can establish and maintain island operation, run a section of the grid independently.
Okay, the synthetic inertia is fascinating. We get traditional inertia, big spinning rotors, kinetic energy stored physically. Can you just quickly recap the practical effect of that physical inertia? How does it help the grid?
Sure. Think of it like a flywheel. The kinetic energy stored, mathematically 1/2 g omega squared, resists changes in speed, which in the power system means resisting changes in frequency. The more inertia you have, represented by the system inertia constant H, the slower the frequency changes when there's a mismatch between generation and load.
Buys time.
Exactly. It gives operators and control systems more time to react. The rate of frequency change, DFDT, is inversely proportional to that inertia constant H. For traditional thermal units, H is typically 3 to 8 seconds. It's an automatic inherent response, but it's limited by mechanical factors. Response times for governor action can be 10 seconds or more.
Right. So if that's the physical way, how do grid-forming inverters pull off this synthetic version with just algorithms? What's happening inside the controller?
It's really clever control engineering. Inside the VSM algorithm, they essentially solve the classic swing equation of a synchronous machine, but in software. There's a virtual rotor equation. The change in virtual speed, d omega dt, is driven by the power imbalance, just like a real machine, but divided by a software-defined inertia constant, H virtual. It's a digital mimic.
And what advantages does this digital approach offer over the real thing?
Several key advantages. First, the inertia, H virtual, is programmable, adjustable from maybe 2 to 10 seconds, sometimes even dynamically. Second, the response speed is incredibly fast in sub-second frequency support compared to 10+ seconds for traditional governors. Third, you get adaptive control. The inertia can potentially be changed in real time based on grid needs. And fourth, they can be programmed to provide really effective damping for those tricky power oscillations between different grid areas, sometimes better than mechanical damping.
The performance numbers must look pretty different then. Speed, accuracy?
Oh, definitely. We're talking primary frequency response within maybe 150 milliseconds from a grid-forming inverter versus 10 seconds or more from a traditional generator's governor. Accuracy. They can regulate frequency to within plus or minus 0.1% compared to maybe plus or minus 0.5% for older thermal units. Plus, flexibility, they can often provide multiple services like inertia and voltage support simultaneously, and availability is typically much higher, often 98% plus, versus maybe 85 to 90% for large thermal plants.
Okay, theory sounds amazing, but where is this actually happening? Let's talk real-world examples. Australia's mandate in South Australia is often cited as a pioneer. What drove that?
Yes, South Australia is a key case study. The driver was unambiguous, the statewide blackout they suffered back in September 2016. That event starkly revealed the system's vulnerability with high levels of inverter-based resources that were predominantly grid-following. It led directly to Australia mandating grid-forming capabilities for new, large renewable projects.
A direct policy response. What specific technical demands did they impose?
They set quite stringent requirements. For projects over 30 megawatts, they need a minimum inertia contribution equivalent to an H constant of 6 seconds. They also require autonomous voltage regulation, the ability to control voltage without relying on the grid, plus a minimum fault current contribution of 2.0 per unit and specific performance metrics for response time and accuracy, all codified in their ASNZS 4777 standard.
And what were the results after putting these rules in place? Did it work?
The results have been quite dramatic. They've documented a 50% reduction in major frequency excursion events. South Australia itself has hit instantaneous renewable penetration levels as high as 93% at times.
93%, that's incredible.
It really is, and it's attributed in large part to these grid-forming resources providing stability. They've also seen significant cost savings over $200 million annually in frequency control ancillary services. Australia is definitely a world leader now in implementing this.
And across their whole national grid, the NEM.
Across the entire national electricity market, they've achieved instantaneous renewable penetration of 68.7%. Again, grid-forming resources are playing a vital role in making that possible while maintaining stability.
Okay, let's shift focus to Texas. After their own grid challenges, ECOTA has seen a massive build-out of battery storage. How much of that is grid-forming?
Texas is another major proving ground. They've deployed over 5 gigawatts of energy storage now, with a huge chunk, 4 gigawatts, added just in 2024. A significant and growing portion of that new battery capacity is equipped with grid-forming capabilities and is actively providing grid services.
And what are these grid-forming batteries actually doing on the ERCOT grid? What services are they providing?
You're doing quite a lot, providing that super fast primary frequency response again, within about 150 milliseconds. They're injecting synthetic inertia, especially crucial during periods when wind and solar output is low and there isn't much traditional inertia online. They also provide dynamic reactive power support for voltage stability on the transmission system, and some are even being qualified for black start capability to help restore critical transmission corridors after an outage.
So ERCOT is clearly recognizing the value. How are they integrating this into their market structures and paying for these services?
They're actively developing market mechanisms. Grid-forming storage can earn revenue from multiple ancillary service streams like frequency response, voltage support, and potentially inertia in the future. They call this value stacking. These assets are getting capacity credit, recognizing their contribution to reliability. They're fully integrated into ERCOT's SCADA systems and their security-constrained economic dispatch engine. And importantly, grid-forming capability is becoming an increasing requirement for new resources wanting to interconnect.
Is there an economic bottom line? Has this deployment saved money or demonstrably improved things financially?
Yes, there are estimates. The American Clean Power Association calculated that the storage deployment in Texas, much of it grid-forming, saved consumers at least $750 million since 2023. That's mainly through reducing press spikes during peak demand periods and by enhancing overall grid reliability, avoiding costly service interruptions.
This all sounds very positive, but I imagine for the engineers listening, especially those working in protection, this must present some real challenges. The fault current is fundamentally different, right?
Absolutely. This is a critical area for adaptation. Protection systems have traditionally relied on the high fault current from synchronous generators, typically 5 to 10 times the rated current, or per unit, to detect and isolate faults quickly. Grid-forming inverters provide much lower fault current, typically in that 1.2 to 2.0 per unit range. It's programmable, and they can sustain it for longer, but the initial magnitude is significantly lower.
So if you're a protection engineer, how does that lower, more controlled fault current mess with your traditional schemes? What breaks?
Several things become challenging. Standard overcurrent relays might not see enough current to operate reliably or quickly, impacting sensitivity. Coordination between protective devices becomes much trickier, ensuring the right breaker trips first. Distance protection, which relies on measuring impedance, sees a different source impedance from an inverter compared to a generator, requiring significant setting adjustments. Even current transformers need to be properly sized for these lower currents. It often requires a shift toward more adaptive or communication-based protection schemes.
Okay, so the challenges are clear. What solutions are being put in place? What's happening on the hardware and system side?
Well, on the inverter side, manufacturers are building in more sophisticated fault response capabilities, like programmable fault current levels and temporary current boosting specifically to help protection operate. There's also a big push for better communication integration, allowing inverters and protection relays to coordinate in real time. And standards like IE and IEC are evolving to define expected fault behavior more clearly. On the protection system side itself, we're seeing increased use of communication-assisted schemes, like line current differential, which are less dependent on fault current magnitude. Adaptive protection is key systems that can automatically change their settings based on which resources are online. We're also exploring alternative principles, like those based on voltage or traveling waves, and developing methods for coordinating the response of multiple grid-forming resources across a wider area.
This clearly needs regulatory support, too. What's happening with NERC standards and FERC orders to guide this transition?
Things are moving quickly there as well. NERC recently issued PRC 029-1, that's in 2024, which specifically addresses protection requirements for inverter-based resources, including grid-forming ones. FERC Order 901 from 2023 includes requirements related to grid-forming capabilities for new resources seeking interconnection. And of course, IEMAFI 147-2018 provides foundational requirements for smart inverter functions, including grid support. Plus, you have the regional ISOs and RTOs developing their own specific rules and performance requirements.
And what are some of the key technical capabilities these standards are pushing for?
They're focusing on enhanced ride-through capabilities, so inverters stay connected during grid faults and frequency events. Also, specific ramp rate controls to manage power changes smoothly. There are tighter requirements for reactive power and voltage regulation performance, and a big emphasis on continuous performance monitoring to verify these resources are actually delivering the grid services as expected.
How are the markets adapting? Are we seeing new ways to actually pay for these grid-forming services?
Yes, that's crucial for incentivizing deployment. Market operators are designing new ancillary service products. Think things like dedicated payments for synthetic inertia provision or for fast frequency response capability, that's sub-second reaction. There are also emerging markets or payments for voltage support services, grid stability contributions like oscillation damping, and even black start service from inverter-based resources.
And is it just about creating new service categories, or is the payment structure itself changing?
We're seeing a move towards performance-based compensation.
Yeah.
So you get paid based on how accurately and quickly you actually regulate frequency, for example. There are often high availability requirements, sometimes with penalties if the resource isn't available when needed, and premium payments might be offered for exceeding baseline performance, like responding even faster than required. The goal is enabling these assets to stack revenue from multiple services, reflecting the multiple forms of value they provide to the grid from a single device.
This has been incredibly comprehensive. Before we wrap today's deep dive, let's just get a quick preview of tomorrow. We're talking control system architecture. How does that fit into understanding grid forming?
It's absolutely fundamental. The control architecture is the how. It's the set of algorithms and logic operating at different speeds that allows the inverter to behave like a voltage source and emulate that synchronous machine. We usually think of it in layers, a hierarchical structure.
Okay, so starting at the fastest layer, primary control, we're talking microseconds.
Exactly. This is the innermost layer, handling instantaneous voltage and current regulation. It's where the core virtual synchronous machine equations are implemented, managing the virtual rotor angle and speed. It also handles basic power sharing with other resources, often using droop control, and provides the very fast current limiting needed to protect the inverter's power electronics during faults. It's almost reflexive.
Then moving up a level, secondary control, operating in milliseconds.
Right. This layer works to restore the system back to its nominal state after a disturbance. It fine-tunes frequency and voltage back to their set points. It can also include functions like harmonic compensation to improve power quality, optimizing load sharing between multiple units, and handling the synchronization process when connecting to the grid.
And finally, the top layer, tertiary control, working over seconds or longer.
This is the highest level, focused on overall system optimization and coordination with the wider grid. It takes signals from the system operator for economic dispatch, manages the state of charge for battery systems, bids into ancillary service markets, and handles communication with the utility SCADA system and energy market platforms. It's the strategic layer.
Okay, bringing it all together then. For the power system engineers listening, what's the big takeaway? What's the bottom line for your work?
The bottom line is that grid-forming technology isn't just another type of generator. It represents a fundamental shift towards a power electronics-dominated grid. This requires you to think differently about everything: how you plan the system, how you design protection schemes, how you operate the grid day to day. Your skills in power electronics, control systems, and communication are becoming absolutely central.
So we're really talking about some major paradigm shifts, like moving from grid following to grid forming as the expectation for new renewables. They have to contribute to stability now.
Exactly. And shifting from relying on mechanical inertia to utilizing electronic or synthetic inertia, it's faster, it's more flexible, but it behaves differently.
Also, a shift from purely centralized control of stability to incorporating distributed control, with these grid-forming resources spread throughout the network.
Yes, that decentralization is key. And finally, a shift in protection philosophy, moving from just reacting to faults to proactively coordinating with these intelligent devices to maintain stability and prevent cascading failures.
It's definitely a transformative time. For everyone listening, think about what this means for the grid's future resilience and for your own role as a specialist navigating this new landscape. The very physics of the grid are, in a way, being rewritten in software. That brings us to the end of today's deep dive. Join us again tomorrow as we unpack the control system architecture that makes all this possible: the math, the algorithms, the real-time challenges of making electrons act like spinning generators. If you'd like to leave feedback or have any questions, feel free to reach out to us at alex.reed.power.podcast@gmail.com.
Or emma.quinn.power.podcast@gmail.com. We'd love to hear from you.